Find the inverse of the following 2 by 2 matrix. So let's get started. We'll label this given matrix as the 2 by 2 matrix with entries A, B, C, and D. Now, in order to determine the inverse of this matrix, we must first check that the determinant is non-zero. So we want to show that the determinant of A does not equal 0. If so, then the inverse exists. So here we go. We know that the determinant of matrix A will be defined as the quantity A times D minus B times C. So we have 6 times 6 is 36, minus negative 4 times negative 9 is 36, and 36 minus 36 is 0. So the determinant is 0, and so matrix A is non-invertible or singular. In other words, the inverse does not exist. So technically we're done, but I want to think about, what is this telling us? So I've mentioned this several times before already, but we're finally ready to explore this. And what this is saying is that since matrix A is non-invertible or singular, this lets us know that the matrix equation has infinitely many possible solutions. So to better appreciate this statement, let's explore matrix A in a little bit more detail. Let's give ourselves plenty of room. So let's begin by simply considering the column vectors of matrix A. So we want to consider the columns of matrix A. Now, we are given matrix A is 6, negative 4, negative 9, 6. So I'm going to label these. I'll say that this first column is vector A sub 1, and our second column is vector A sub 2. So let's think about these vectors. Column vector A sub 1 is 6, negative 4. And I'm noticing, hey, both entries in this vector have a common factor of 2. So let's pull that scalar multiple out. So we have 2 multiplied by the column vector 3, negative 2. Beautiful. Now what about column vector A sub 2? So vector A sub 2 is negative 9, 6. Now here, keeping our first column vector in mind, what happens if we pull out a scalar multiple of, say, negative 3? What does this leave us with? Well, we're left with the vector 3, negative 2. So what are we observing here? We're observing that these vectors, vector A sub 1 and vector A sub 2, are scalar multiples of each other. Now, since we're only considering a set of 2 vectors, and we have shown that those 2 vectors are scalar multiples, we can make the following conclusion. So we can say that, therefore, since vector A sub 1 is a scalar multiple of vector A sub 2, and of course is such that C is any scalar, then the columns of matrix A, and so the set containing vector A sub 1 and vector A sub 2, the columns of matrix A are linearly dependent. So let's think about what this is telling us, that the columns of matrix A are linearly dependent. What does this mean? So we want to think back to our definition of linear dependence. So this implies that the vector equation, defined as scalar x sub 1 multiplied by column vector A sub 1 plus scalar x sub 2 multiplied by column vector a sub 2 being equal to the 0 vector has a non-trivial solution. So if this vector equation has a non-trivial solution, this means that at least one free variable exists. So what does this mean? If a free variable exists, then the homogeneous equation, matrix A times vector x equals the 0 vector, has infinitely many possible solutions. So all of these are equivalent. We're using the definitions that we've already established for systems of linear equations to help us better understand what a non-invertible matrix means. What is it telling us? So if matrix A is non-invertible, we know that the matrix equation will have infinitely many possible solutions, and that the columns of matrix A are linearly dependent. Now, what's really fun here is we can take all of these conclusions that we've just made about non-invertible matrices and relate them to invertible matrices. So let's take a look. So let's start here by simply recapping what we've just discovered or shown. So we know that for a 2 by 2 matrix A, if the determinant of matrix A is equal to 0, then matrix A is non-invertible or singular. In other words, the inverse does not exist. Now we've also just shown that if matrix A is non-invertible, then the columns of matrix A are linearly dependent or form a linearly dependent set. And now by definition, if the columns of matrix A are linearly dependent, then the corresponding homogeneous equation has a non-trivial solution, implying that a free variable exists, and the homogeneous equation will have infinitely many possible solutions. So what I'd like to do now is take these conclusions and think about them in the opposing direction. So for a 2 by 2 matrix A, if the determinant of matrix A does not equal 0, then we know that matrix A is invertible or non-singular. So if a matrix is invertible, this lets us know that its inverse exists. Now, using the conclusions above, since matrix A is invertible, this lets us know that the columns of matrix A are linearly independent, or form a linearly independent set. And again, using the conclusions above, here, since the columns of matrix A are linearly independent, this lets us know that the corresponding homogeneous equation, matrix A times vector x equals the 0 vector, has only the trivial solution. So this implies if the homogeneous equation has only the trivial solution, there are no free variables, and the homogeneous equation is going to have one unique solution. And what's great here is that these new fun conclusions not only apply to homogeneous equations, but they apply to non-homogeneous equations. So we need to now go ahead and establish a more formal theorem to define what we have discovered here.